Okay, so today is a special day. Not only is it the day after Valentine's Day, but we get to talk about continuous distributions. But not only that, as a special bonus, we're not going to talk about just one continuous distribution. We're going to talk about two today. Okay, so we're in 7.1, we're going to talk about continuous distributions. Okay, so specifically, we're going to talk about the uniform distribution, and we're going to talk about the normal distribution. Now, before we do that, I just want to emphasize, oh, I'm not getting this, there we go, on video. Let's just remind me, what does discrete mean? Discrete means whole numbers. And continuous means everything else. Everything else. Okay? Now, there's going to be something, the one thing I always like to tell people, the uniform distribution is going to be so easy, it's going to blow your mind. And then the rest of this chapter 7, we're going to talk about the normal distribution, and then come test, you're going to think everything's a normal distribution, and it's not. Okay? So don't forget this because it's so easy. Okay? So just a reminder, well, I'll do that in a minute. Okay, let's talk a little bit about the uniform distribution. This is a random variable. X can take any value between two values. Okay? So typically with a uniform distribution, it's basically going to be a rectangle. Okay? That's what it looks like. It's just a rectangle. Now let's do an example here. And let's say that you have a friend that is always late. Do you guys have a friend like that? My wife does, it drives me crazy. Okay? We always say, hey, come an hour early so that then she might be on time. Okay? So at any rate, your friend, maybe I should back up. Your friend is always late up to 30 minutes. And my wife's friend is more like an hour, but we'll just go with 30 minutes, okay? She is just as likely to be 5 minutes late as 30 minutes late. Okay? All right, so the last thing I want to do is say find the probability that she is 10 to 20 minutes late. Okay? All right, so if this is a uniform distribution, she could be just randomly late any numbers, so she's going to be between 0 and 30 minutes late, right? Okay, so I'm going to draw my graph like that. Now, we know that this is a rectangle, right? And we also know if it's a probability distribution function, what should the sum of the probabilities equal? It should equal 1, right? And all of your probabilities should be between what two values? 0 and 1. Okay. So if we're looking here, and if the sum of all probabilities have to equal 1, okay, and we know that this is a rectangle, what's the area of a rectangle equal? What's that formula? Length times width. Okay, so if we know that the area has to equal 1, and we know that the length, what is this length here? That's got to be 30. So what does the width have to be? 1/30, right? So the width has to be 1/30 in order to satisfy that rule there, right? Okay, so you should be able to figure out how tall any rectangle is. In this case, it's 1 over whatever your length is. Okay, super easy, right? All right, so in this case, we want to know that she is 10 to 20 minutes late. So we want to know this area here in blue. Okay, so Kendall, if area is length times width, what's my length? 10. So if my length is 10, and I'm going to multiply that by my width, and my width is 1/30, right?
Oh, yeah, 1/30.
1/30. So the probability that she is between 10 to 20 minutes late is 1/30. 1/3. Okay? Piece of cake? Yes.
So it's uniform distribution if every possibility is equally likely.
Every possibility is equally likely. Yes. Okay? Now, let me ask you a trick question that's so easy you're going to miss it. Okay? What's the probability that she's 10 minutes late? What's the length from 10 to 10? The length is 0. What's the height or the width? 1/30. So 0 times 1/30 is 0. Okay? Because she has no length, right? It's the line. It's not actually a rectangle. Okay? So the thing that I want to point out here, yeah, I think. Okay. On a discrete distribution, you can have a number like probability of x equals 3, right? And it will equal some value. Somebody make up the value.
6.
No, it can't be 6.
0.6.
0.6. It could be 0.6, right? Okay. With a continuous distribution, what's the probability that x equals any value such as 3? It's 0. Okay? So we need to make a big distinction between discrete and continuous. In a continuous distribution, whether it's normal, uniform, any other continuous distribution, and we're going to deal mostly with continuous. We're done with discrete in this class. The probability that a discrete can equal a specific number, a continuous, if it equals a specific number, the answer is always going to be 0. Okay? So once again, from 10 to 10, 10 minus 10 is 0. So you've got no length. Okay? So that's true with any continuous function. Okay? In order to do any probabilities, you've got to come up with some sort of a range. 10 to 20 minutes, 10 to 15 minutes, something like that. 3 to 7 minutes. Okay? Does that make sense?
Why would it only be equal? So then what difference between a discrete and continuous and you graph it then?
So if I were to graph it, let's say here, somebody asked me that in my other class too. So if I were to graph some sort of a discrete distribution, whatever, it looks like this. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? Let's say that's 0.1, 0.2, 0.3, 0.4. Okay? Let's say that I want the probability that x equals 3. Okay? This is a discrete distribution as opposed to a continuous distribution. If x equals 3, it's just the area of that rectangle there, right? What's my length? 1. What's my width? 0.4. So the probability that x equals 3 is 0.4.
That's discrete.
That would be a discrete.
So what about continuous?
So continuous, the probability that x equals 3 is 0 because that has no length. It's got width, it has no length.
is not between 10 and 20? Why would that happen?
I could say the probability that x is between, sorry, probability that x is between 2.9 and 3.1. What would that be? What's my length? 0.2. What's my width? 1/30. So 0.2 over 30, whatever that is, which is 2 over 60, which is 1/30. Is that right? No, 2 over 600.
115.
115. There you go. Okay?
So then, though you said that the only number that a discrete could equal would be 0.
No, I said for discrete numbers,
Or, sorry, not
you can
discrete,
get x
continuous.
equals 3 and you can get a value.
Right, but
For continuous distributions, if you pick a specific value, the value is always going to be 0. Okay? Don't think about that too hard. Just trust it. Okay?
Basically, like, you can't find the area of the line. It's just a line.
Perfect. No, I'll say that louder. You can't find the area of a line. That was an excellent explanation, Shay. Okay? All right. So we're done talking about the uniform distribution. Okay? We're going to talk about the normal distribution from now on. Okay? Now, interesting little tidbit about the normal distribution. It's actually called the Gaussian distribution. Okay, it was discovered by a guy named de Gauss. I don't know how you spell de Gauss, whatever. I probably spelled it wrong at least once. Okay, so, funny story. Apparently, Mr. de Gauss had a mathematical rival. He didn't want to call it the Gaussian distribution. He says, no, that's just normal data. I'm going to call it the normal distribution. Well, for whatever reason, that stuck. And so that's why we often refer to it as the normal distribution. You're familiar with the bell curve. Okay? It's the most common distribution in statistics. It's our favorite. Okay? We love it way more than uniform, even though uniform was easy. All right, so let's talk about some properties. Properties. Okay, number one, it's symmetric about the mean mu, okay, which is going to be right there, mu. Okay, the Greek letter M, I guess. Looks like a U with. Anyway, number two, the mean equals the mode equals the median. Oh, I'm not getting any of this on video. There we go. You guys got to tell me I'm not getting on video. Number three, it has inflection points at mu plus sigma and mu minus sigma. Who remembers who's had calculus? Do you remember what the point of inflection is? There you go. Very good. Okay, so for those of you who didn't hear because he was kind of quiet, it's where it changes its concavity from concave to convex. So that's going to happen at +1 standard deviation and -1 standard deviation. Now that also happens to be a very important point. And we know the 68, 95, 99.7 rule. That's my favorite name. But what it basically tells you is that 68% of your data is within 1 standard deviation. And I'll bet you can tell me what's within 2 standard deviations. 95%. And I'll bet you can tell me what the next rule is. 99.7% of your data is within 3 standard deviations. 99.7% of your data, okay? Sometimes it's called the empirical rule. I like the 68, 95, 99.7 rule because we can't forget it, right? Okay? All right. Number 5, what should the sum of all probabilities be under the curve? Should be 1, you already knew that rule. Number 6, 50% of the area is on each side of the mean. And number 7, at extremes, the graph approaches 0. Okay, and you can see that here. It's very close to 0. I made it look like it goes there, but it doesn't. It just gets really close.
What does number 6 say?
Number 6 says 50% of the area is on each side of mu. So you've got 50% over here, you've got 50% over here. Okay? Oh. Now, isn't that a nice looking curve? Would you like to know the equation behind that curve?
Yes.
How's this? Y equals 1 over sigma times the square root of 2 pi e to the minus x minus mu squared over 2 sigma squared. 2 pi sigma squared. So a nice looking curve, a very ugly equation. Okay? Now, if you're in
So which one
calculus, I'd
was?
make you integrate that.
That's 2 pi r squared from the very.
2 pi sigma squared. Actually, do I need a square root in there? You don't need to know that. That might not be quite right, but it's close. I think there's a square root. In fact, I think there's a square root here. I think the square root is right there. That's a negative there. I'm pretty sure that's right. Anyway, if it's wrong, I'm sorry. You don't need to worry about that in this class. If it was in calculus, I'd worry about it more. All right. So now the other thing that I want to mention is we have a special curve, which is called the standard normal curve. Okay? And emphasis on the word standard. Okay? So, standard normal curve follows these same 7 rules that I gave you, except for we've got two more special rules. Number 1, the mean is always 0. And number 2, the standard deviation is always 1. Okay? And you can convert any normal distribution to a standard normal distribution with the equation z equals x minus mu over x minus mu, I say. I said it, I wrote it wrong. Over sigma. Okay? What's going to be your favorite equation this chapter? Besides area equals 1 times width. Okay? In fact, you'll use this one a lot more than area equals width times width. Okay, so here's what I'd like to do. Oh, we're doing a lot better on time than I did in my other class. Okay, so let's do an example. I'm going to go back over here, I think. We're going to erase all this stuff. Okay, I'm going to erase the uniform distribution, which means don't erase it from your brain now. I'm going to give you a quiz on Tuesday because there's no school on Monday. And I'm going to put a uniform distribution, and I want you not to miss it. And I want you not to miss it on the test. Okay?
So how do we distinguish between the two? Just if it gives us one value, or if it gives us like a rate, like a.
Well, it will tell you it's a uniform distribution, looks like a rectangle. The normal distribution looks like a bell curve.
Okay.
Okay? All right, so let's do an example. You want to know probability of finding a toddler 35 to 38 inches tall. You know it is normally distributed with a mean equal to 38.72 inches and a standard deviation of 3.17 inches. Okay? All right, now, first question is, in fact, I'm going to make this a little bit easier. I will use this 3.17 a little bit in a minute, but I want to make this a little bit easier, so I'm going to erase the decimal for a minute. Okay? We're just going to make the standard deviation 3 inches. First question is, find the values for the 68, 95, 99.7 rule. Okay? Now I'm going to introduce to you a new phrase. Okay? You've probably heard the initials WWJD. What does that stand for? What would Jesus do, right? Did I say this already?
Yeah, you draw a picture.
Draw a picture.
Okay, draw a picture. What would Rick do? Rick would draw a picture. Okay, we're drawing a picture. Okay, what should be the mean? My other classes acted like they've never heard that before. I'm going to set it here, not there. Okay, well, I'm glad you guys do. Say it again. The mean is 38.72. Okay, if we go one standard deviation away, what are these two values here?
35.72.
35.72 and 41.72. If I go 2 standard deviations away, these values are 32.72 and 44.72. And if I go 3 standard deviations away, I'm going to get 29.72 and 47.72. Okay, so we've got that done well. All right, now let's go back to the question. I'm going to put my 3.17 back in here, okay, because is the way I want to do it. And I want to know the probability that a toddler is 35 to 38 inches tall. Okay, so if I'm looking here, I've got one more color. So 35 inches would be about right here, and 38 inches would be about right here. And I want this area here. Right? All right, now, that might be hard for me because it doesn't follow the 68, 95, 99 rule very well, does it? Can I use the Z chart? Yes, how do I use the Z chart? Find my Z equation with this equation right here, right? Okay, so I'm going to use that, and in this case, what I'm going to do, I'm going to erase this.
How do you do X if you're looking for a range?
Yep, I'm going to show you right now. That was a great question. Okay, so we want the probability that X is between 35 and 38 inches tall. So the first thing I'm going to want to do is I'm going to find the Z-score for the 35. Okay, so I'm going to plug it into this equation here. I'll write it here, X minus mu over sigma. So for the 35, I'm going to get X, which is 35, minus my mean, which is 38.72. I'm going to divide that by 3.17. Okay, which gives me negative 3.872 divided by 3.17. So my Z is going to equal negative 1.17. Okay, now I'm going to do the same thing, but this time I'm going to do it for the 38. Okay, so TJ, how do I do this?
you use the value.
You don't know how to use it? Okay, so what do you think X is?
Where's our value?
I'm using the 38.
30. Okay, so 38.
38 minus what's the mean?
38.
38.72. I'm going to divide that by,
Second division.
which is
3.17.
3.17. Okay, so that works out to be negative 0.23. Okay, so here's what's going on here. So I just converted these both to a standard normal distribution. So instead of having this, here's what I'm going to do. I've now converted this. Unfortunately, I can't use any of those 60. There's going to be a lot of questions that deal with the 68, 95, 99 rule. There will also be some questions that are going to ask you to convert it to a standard normal. So I've got a 0 here. This is negative 1.17 standard deviations away. And this is negative 0.23 standard deviations away. I want this area here, okay, which matches this area here. Does that make sense? Okay, so here's what we're going to do. Now, how many of you do not have a copy of the formula sheets in the back of your book because you bought a used book and somebody tore it out? Okay, so for those of you who that applies to, if you go to the announcements back on the first day of class or even before, I've got this thing called book tables. Open that up. These are all the formulas that you're going to have for the class. Okay, so what I've got here, two things I want to show you really quickly. I know we're out of time. Two things I want to show you are, first of all, notice the graph here. This gives you the area to the left. In a future chapter, we're going to learn about the t-distribution. It gives you the area to the right. So you need to understand, am I getting the left or am I getting the right?
The t-distribution?
Yeah, we're not learning that today, but we will. So I just want you to pay attention to the graph. Okay?
Area on one is easy.
Huh?
Area on one is easy.
Yeah. So at any rate, here's what's going on. I got two z-scores, negative 1.17. So here's how it works. I'm going to go here to negative 1.17 is this column here. So negative 1.17 gives me that value, 0.1210. So what this is telling me, the area to the left of negative 1.17, this area here is 0.1210. Okay? Now I'm going to do the same thing for the area negative 0.23, because that's my other z-score here. So when I go to negative 0.23, negative 0.23, that gives me 0.4090 there. So this area here is 0.4090, okay? So I can take this number, I can subtract this number, and it will give me this area here, which works out to be, what I wrote this, 0 minus 0 is 0, 9 minus 1 is 8, 9 minus 2 is 7, 3 minus 1 is 2, 0.2780. So the probability that you find a child between 35 and 38 inches tall is about 27, almost 28%. Yes?
So the reason why we did the standard deviation with just 3 is because we don't really use those standard deviations.
Well, no, I should have left this at 3.17. So you should don't round it.
Really
I was just trying to keep it easy for you so you could do the math in your head.
theoretically, in the math, again, that doesn't come into play at all.
What doesn't come into play?
Because when we convert it to a standard.
Yeah, so we're converting this. Now realize we're converting 3.17 to 1.
That's my point. So
Yeah, so it's going to have standard deviation
that's
of
just
1.
the visual giving you an idea.
Right.
Really, the math doesn't matter.
All right, so I will post this up on Canvas over the weekend. Tuesday is on 7.1. We'll probably cover some more of 7.1. See y'all on Tuesday.
So on the quiz, we probably won't expect to have anything like that. We'll have to use the table, right? Or,
You'll have to use the table, that's right.
so you will hand that out on the quiz then?
I will hand that out on the quiz. No, you have to memorize that.